Hello and welcome to the Advent of Code 2021, day 12, part 1. So today we have one of the problems that is my favorite kind of problem, which is a path graph problem. Essentially, we are giving a path description in this form. So we have the list of edges in the graph, and by interpreting it graphically, we can get a graph like this, in which we have a start and end position and a set of nodes that can be connected to form a more complex graph. We do not have more drawing, but can be much more complex. In this graph, except the start and end node, every node is represented by an uppercase or lowercase string. For example, here we see that there is uppercase A, but also lowercase b, and so on. And the problem is asking us to count how many possible distinct paths are there that go from start to end, with the rule that every lowercase node, for example d in this case, can be visited only once in a path, while the uppercase nodes, like this uppercase A, can be visited multiple times, an infinite amount of times in fact. So for example here we can do start A end, that's valid, and we can have start A C A N, that's also valid because we can pass twice by A. We can have start B end, start B A end. We cannot, for example, have start B A B end because B is lowercase and we can go through it only once. Likewise, we cannot have start B D B end because we would have to necessarily pass twice by lowercase b, which is impossible. So the question that the problem asks is how many distinct paths are there that can visit small caves at most once. So we ignore how many times we pass to a uppercase cave. Cave are nodes in this problem, but lowercase caves can be visited only once. And as before, instead of starting straight away with my solution, I think it's easier to start with the problem, the small example given by the problem, so that I can directly compare my my solution with what the problem shows. And once I'm sure that it works on the sample problem, I can directly apply to the input. So I already copied the sample input in here. This is the one in the problem, so not my input, but the one that is given here, because I already know what is the solution, so I can compare it. And let's process it. So first we have to read this input into something that makes sense to us. So let's think about data structures. What is the best way to represent it? To decide the data structure, in general, I think about what I have to do with this data. And in this case, what I have to do to explore the graph, to decide how I can move in this graph, is to know what are the nodes that can reach from a given one. So essentially, this data structure will contain always what are the nodes that can be reached by a specific one. So it's a dictionary where the key is the starting node and the value is a list of nodes that I can reach from that. So for example, DC is a node that can go to end, start, or hn. So what I want to do when I explore this graph is just to know this, to know what I can reach from DC. This way, a dictionary seems just the most logical way to interpret this data. So here I already created the scaffolding code, as usual. To save time, I iterate over the lines. So for line in fr. Now, a line is simply two strings of English alphabet characters separated by a dash sign. So I can partition the line. Partition is equivalent to split, but directly returns me a tuple of three elements, which are the part before the dash, and the part after the dash. I can use it instead of split just because I know that there are already two and only two elements here. So I trim the line. Split. No, what is the name in strip? Trim is JavaScript. Then I partition, passing a dash. Partition, you can see from the description, will give me a tuple of three elements, which are the start, the not the comma that I don't, the dash that I don't care about, and the end. Now what I want to do is to create a dictionary of edges. Initially it's an empty dictionary, and then every time I see an edge in the list, I check if the edge is already in the list of edges. If it is, I simply have to add this new end that I found to the list that is already there. So I say that edges from the starting node S will receive a new element, which is E, so the ending. Otherwise, I simply create the initial list, which is containing only the ending E. So this is simply a representation of the data that is nicer for the usage that we will do later. Now I can just print the edges so they can see how it looks like. Okay, so this is the dictionary of the edges. For example, I can see that DC, lowercase, goes from end, start, hn. So I click on DC, I see that it goes to end, start, hn, that's correct. Hn goes to start and end, that's correct. And so on, seems good. Now let's go to part 1. So part 1, we receive the edges in here. We can remove the print. What does it have to do? So this is a graph exploration problem, which means that my solution in general is to create a set of all the solutions and then iteratively try to expand this set, finding new solutions, and I stop only when I cannot expand anymore, which means that I found all the solutions or there is a bug. So what is the solution? So the solution initially is a list containing only the starting point. We know that we have to start from the start, of course. Then what we do, we will create a new list. So in pseudocode we say, okay, while true, we create a new list, which initially will be empty. Here we will put the code to calculate all continuation of the solution and put them in new list. And then, so here there will be some code, and then we say, okay, if new list has same size of solution, stop, because it means that after trying to expand every possible solution that we already know, we didn't find anything new because the new list has the same size, then we stop and we return the length of the solution. Because the problem was asking us what are the possible paths that can that are just in that are in the final list. So let's go to the new list, let's go to the solution and try to expand every possible value. I did an error because the solution will be a list of paths. So not just a list of nodes, but a list of lists, where every list contains a set of nodes. So this was wrong. Solution is a list of lists. So now what I do, I go for every path in a solution and I try to expand it. Every time I can find an expansion, I add it to the new list. How can I expand it? So first of all, I say that if the path already reached the end, so the path already has as the last element the end, I simply keep it as is, because that path is complete. We cannot do anything. So if path at -1, even better, I call it last node because we will use it later, is the last element of the path, so the one that we actually can see from which we continue that path. So if this last node, not nodes, is equal to end, what we do, we just keep it as is. So we add to the new list, we append the AutoZit path, so we just keep it, and we continue. Why? Because this is a path we already explored. So the new list now will contain the same path that already reached at the end as this, because that's a complete solution. We cannot do anything about it. Otherwise, we have a path that we can expand. So let's say that we want a list of continuation. So we want to say that for continuation, let's say candidate next, in what is it? We forgot to pass the edges to the list. So we take all the possible nodes that we can reach from the current last node, and they are all the possible candidates. So what can we do from a candidate point of view? We have to check whether that candidate is start, because if it's start, we ignore it. So if start, ignore it. Actually, I'm not sure. Does it say anything, the input of the problem, about passing again from start? It doesn't. Okay. Okay, does it say, okay, so let's say that if start, I ignore it, because here it doesn't show any path with the start in the middle, so it's always the starting point. So if start, we ignore it. If lowercase and already there, ignore it. Otherwise, keep it. Expand and keep it. Okay, I just noticed a small error, which is that in our list we always have the path in a single direction. So we have these edges, as we have in this example, as if they went from, for example, from B to D. But we know that actually they go in both directions. So essentially, when I ingest the input here, I'm assuming that I go from DC to end, but I can also go from N to DC. This is not useful, but for example, I can go from HN to DC and to DC from HN. So I have to change a bit the code that I ingest the edges to append the data in both directions. So I repeat the same code, swapping the start and end. So if E S, this is something that I would have realized it later doing debugging. This can also be simplified a bit, because for example, who cares? No, let's keep it like that. Yeah, this can be simplified a bit. I can say edges s equal edges dot get E, and if I don't get it, I get a empty list dot concat a list containing E. Yeah. So essentially, this code is simply say, okay, the edges that start from S will be the edges that already had. Sorry. Plus the list containing E. So simply add to the list E, but also if you don't find it, assume that it's an empty list. So this is just a shorter way to do this. If it's already there, add it, otherwise keep it. It's not doing anything anything fancy. It's just a short way. So this operation says, okay, the edges of value S will be what you find already for S plus the edge E. But if you don't find it, use an empty string as the starting point. So it's just a short way to build this graph. And we do it both directions, so from S to E and from E to S, because these edges are bidirectional. Okay, so back to our solution. We wrote the pseudocode, so let's check it. So if the candidate, so if start, ignore it. Fine, this is easy to do. I say that if the candidate next is equal to start, continue. Nothing strange. Lowercase is a bit weird, because first I have to check that something is lowercase. So I said if candidate next dot, I don't remember if in Python there is already a function to do that, so let's see what happens. Is lower, maybe? Yes, so there is a function is lower that does exactly that. Okay, and it works. So if candidate next is lower, we have to check if it's already there. So is it already there? We can do it in a single operation. So we say that if candidate next is lower and candidate next in what is it, path, continue. Very simple. And now if these two didn't continue, it means that we found a valid continuation, and so we simply add to the new list the path. So we say that new list dot append what the current path plus the new node, which is the candidate node, candidate next, and that's it. So now to recap, what we did is we start with a solution which is just a list containing only the node start, and then we try all the possible expansions and we put them in a new list. So if the node is already at the end, if the possible solution is already at the end, we just keep it as is. Otherwise, we try to expand it. And to expand it, we simply have to go through all the possible nodes that we can reach from the last one. So basically, all the way we can continue this list of movements and check that they do not reach the start. Again, because that's apparently forbidden but is not stated explicitly in the problem. And they do not visit twice the same lowercase path. So if the next one is lowercase and also is already in the path, you just continue. If not, you just append this value to the list. Now we have to check whether this list has the same size. So essentially, if we found solutions, so we say that if the length of what did we call it? Not new list. New list, yes, is equal to the length of solution break. Otherwise, the solution is the new list. And now, what I want to do after all this operation is to return the length of the solution. But there is a small problem, which is that this solution will contain also weird cases that we have to ignore. So I'll also print the solution so that I can already do some troubleshooting. So let's run it. Maybe it's easier if I print them one by one. So I say for sol in solution print sol, so it's a bit more readable. Okay, so here there are 19 solutions. Is it the correct number? Is it? Hmm. 19. Yes, so the number seems correct. For example, start, hn, end. Is it here? Yes. So it seems that we already have a solution that is viable. 9. Nice. Let's try it with the bigger example, which is here. This f, s, and blah, blah, blah. So I'm simply trying the sample problems that are in the list, in the description of the problem. 2 to 6 is the solution here. So this is 2 to 6. Yes, so it's nice. It seems that we already have a solution. Let's try now with my actual input problem. So this is the real solution. I run it and I get 4912. So let's see if it works. 4991. Oh, I already forgot the number. 4912. Okay. And it works. So let's recap a bit what we did because there was some abstraction. So first of all, we get a list of all the possible edges. So how every cave is linked to the other. We read this list and parse it as a dictionary that for every edge, for every node, so every cave name will tell me what are the possible, all the caves I can reach from that edge. Then I noticed that the connection is bidirectional, so I have to actually put start and end and swap them. So I simply do this operation twice. This is just a short way to say if it's there, add it, otherwise create an empty list with that value. And then I enumerate all the possible solutions. So basically all the possible paths, and I keep trying to expand them. So I keep saying, okay, you have this path, you already found it. How can you continue this path? It's simple. If it ends with end, you don't continue, but you keep it because it's valid. And if you have a next way to continue, so if in the dictionary of all the nodes we found a node that we can reach from the current one, we say, okay, if the next node that you can reach is start, ignore it. If the next node that you can reach is lowercase, so it's one that you have to visit only once and is already in the current path, you ignore it. In all the other cases, you just append it to the list. Notice that appending, we are creating multiple multiple paths from the starting one in case we find multiple candidates, so we increase the size of the solution. We do that, and after doing all of this for all the paths, we check whether the new list that we created has the same size of the old one. If that's the case, it means that we didn't find any possible expansion. The new list of paths is exactly the same as the old one, so we break. If not, it means that we found something new, so we have to keep trying to expand to find new solutions. So we simply put the new list back into solutions. And here, after doing all of this, it means that we did break from the cycle, so we found all the possible solutions. We print them just for the sake of the human, that is me, so that they can see the solution, and then we just return the length. And that is the solution for part 1. See you for part 2. Bye!